tree to satisfy all the properties? Well, actually, here's a way to do it. The leaves are black. These nodes are black. This node is red. It satisfies all the properties. That was easy. By the way, how do we look up nodes in a red-black tree, right? We want to look up, I don't know, 10. Well, 10 is greater than 7, we go right. 10 is greater than 9, we go right. 10 is less than 12, we go left. We reached a leaf, we return the default value. Notice that the lookup function ignores the colors. That's convenient. Makes it nice and easy to implement and prove things about. Let's insert 8 into this tree. So it goes there. That's the easy part. What color should it be? Well, red seems to work. Fine. Let's insert 11. Goes there. What color should it be? Can't be black, because then the number of nodes on the path to 11, or to the leaf of 11, is 4. The child of 11 is 4, whereas the number of nodes to the child of 5 is 3, black nodes. So it can't be black. That would unbalance the black nodes. It can't be red, because then we'd have 2 red nodes in a row. So we have to recolor. So we'll recolor. 12 will become black. 11 is now red. This is okay. Insert 10. 10 goes here. That's the easy part. Can't be black, because that would unbalance the black nodes. Can't be red, because then there'd be 2 red nodes in a row. We can't recolor 11 black, because then we'd still have unbalanced black nodes. This tree cannot be colored with red and black. So we have to do a rotation. So here's a rotation. The notion of rotation goes all the way back to 1960, Adelson, Bielski, and Landis, right? That here's a tree with keys X and Y and subtrees A, B, and C that are in between the X and Y in this order. And here's a tree with X and Y and subtrees A, B, and C that go in between X and Y in the right order. And these trees are just a very local transformation of rearranging the pointers. And so we can do a right rotate to get from this tree to that tree, or a left rotate to get from that tree to this tree. Okay, so if we rotate left about node 9, so we're moving 9 and 12. Now the subtrees rooted at 8 and 11, we're not going to touch their interior. This is a very local transformation. So there we are. We rotated left about node 9. Okay, so the basic idea is that by doing one rotation, or just 1 or 2 rotations, locally, we can recolor. So here's the implementation of red-black tree insertion with rotate. Ooh, there's a lot of pointer update here. Let's not do it this way. Let's do functional programming. Okay, so, all right. So when we insert new nodes, we've got to rotate in some way and recolor. And that's red-black trees. And it's actually complicated, the rules for exactly how you rotate and recolor. But there are a finite set of rules. And what we'd like to be able to do is prove the correctness of red-black trees without actually having to learn the rules. And you'll see how easy that's going to be. Okay, so that's red-black trees. And now we can implement it in Coq. So the way we write down the Coq program for red-black trees without actually understanding it is to read Okasaki's paper. Chris Okasaki, in his PhD work at Carnegie Mellon, did a lot of functional programming of efficient algorithms. And this paper shows, how to implement red-black trees in a pure functional programming language. I think it was ml when he did it, so we'll just translate the ml to coq without understanding it. And here's how it goes. So we'll have a tree type. This is just like the previous tree type we had for ordinary search trees, except now there's a color in every T node in addition to all the other things that we had there. And the lookup function for red-black trees is just like the lookup function for ordinary binary search trees, and we ignore the color. This underscore is pattern matching the color part of the tree node. We're using LTB here instead of some other less than, just because we've chosen to do this in the abstract way that we can extract to OCaml. But this is just the total ordering on keys, less than. So that was easy. And then here's a balance function. RB is a color. The idea is to build a node with color red or black, with left child T1, with key K binding to value V sub K, and right child T2. So really, we could just put capital T on all these arguments. That's the idea. But capital T might give us an ill-formed tree in the sense that maybe there's two red nodes in a row or something. So balance is going to be just like capital T, except it does whatever local transformations it has to make sure that the red-black property is preserved. And here's what it has to do. If the color is red, then that's fine. Just build the tree. Somehow we know that T1 and T2 start with black nodes. But if the color is black, that's this case, then we might somehow be unbalancing the black nodes in the tree. So let's look at the left subtree. And if it has two red nodes in a row like that, then we'll do a construction like this. We'll recolor its inner nodes to be black. And if tree T1 has two red nodes in a row like that, in other words, the right-hand child is red, then we'll recolor its black its nodes like that. And otherwise, if T2 has two red nodes in a row, we'll recolor to black, and so on and so forth. Now in there, I think there's a rotation somewhere, right? Because the tree we're building here, we meant to build a tree with K at the root, right? But this tree that we're building here has Y at the root, and it has K in the left child. So we have done a rotation. Okay, that's the balance function. Raise your hand if you really understand it. I'm not raising my hand, you notice. Okay, so far we're trusting Okazaki. But much as we respect Chris Okazaki, we don't want to have to trust him. So we're going to prove that this is correct. Okay, now here's an easy function. Make black of T, takes a tree, and colors it black. So whatever color it was, just make a tree just like it, but with a black color. And now insert in a binary search tree, ints. In tree S, we'll bind X to Vx. So if S is the empty tree, we'll make a red node with empty leaves, empty children rather, that binds X to Vx. But if it's some tree with key Y, well, if X is less than Y, then we'll insert X in the left child and make a tree that looks like this. This is exactly the tree you would expect in ordinary binary search trees, but we'll make the rebalanced version of it. And so if you read balance as a capital T, right, you get plain old binary search trees. And if we believe that the balance function returns a roughly equivalent tree, but one that happens to be in balance, then you can understand this insert function very easily. So raise your hand if you understand the insert function. Yeah. Okay. So, and then insert at the root says do this recursive function ints, and then if the root happens to be red, just color it black. And coloring the root black doesn't change the balance condition on how many black nodes there are in any path from the root to a leaf. That's perfectly okay. Okay, so now let's prove some theorems about red-black trees. This theorem says T is not equal to E. That's easy. Okay, useful. This says if we insert something into a binary search tree, it's not empty. We'll need this for proving things about the balance condition. So let's destruct the tree, and in the case where the tree is not empty, we can just apply T not equal to E. But now here's the hard case where the tree was, excuse me, I guess, yes, right. So here we have insert in some tree and a balance of an insert, right? This is just from the definition of insert. And so we don't have to do this by induction. Here's why we don't need induction for this theorem. No matter how big that tree is, insert will build one node at the top that's a T, and that's already not E. So, and rebalancing, well, we might have to reason 2 levels down to reason about rebalancing, but only 2, because rebalancing only touches the first 2 levels. So we don't need induction. We're going to remember the result of insert is A1, and now we can just do this as a theorem about the balance function. We sort of believe that the balance function always returns a T. And so we don't even need to know anything about the value of A1. So let's unfold the balance function. And now, let's see here. Here's our proof obligation. We have to prove that this whole tree is not empty. Okay? Well, the balance function turned out to be more complicated than we thought. Good thing you guys didn't raise your hands to claim to understand it. Okay. Part of the reason it's so long is that when you actually expand the Calc pattern matching, where you had an underscore, Calc really has to list every possible case. Right? Okay, so how do we prove this? Well, let's do it by case analysis. Either that's true or not. So let's destruct LTB xk. Notice we're not even using bdestruct. We don't care whether it's actually less or greater. We just have to handle the 2 cases. All right, so we destruct that. Now we have 2 cases. Well, all right, let's do this by case analysis on the color. If the color is red, okay, then that's easy. We just apply T not equal E. But if the color is black, then we have this case analysis on A1. So let's destruct A1. But now we have this case analysis on S2. Let's destruct S2. We could apply T not E here, which is what we should do, but for some reason I've done intro and inversion. That's fine. Okay, here we have a case analysis on C. The first time I did this proof, I typed and I typed and I typed and I typed, and there were more and more cases, and I thought, oh, maybe I need induction. Maybe I'm unfolding some induction by hand infinitely. But no, I was unfolding finitely a big case analysis. So let's use a little bit of tactical proof automation to manage the case analysis. So here's a tactic program in the LTAC programming language. Match goal. So we're matching the goal, which is everything above and below the line. And this turnstile here, this bar just represents alternate cases. So the bar you're used to in a match. This is the match of LTAC. It's not the match of Galena, of the actual logic. This is the match of the tactical programming language. They're different. They only have the same name so as to make it confusing. This is the match of the underlying logic. Okay, now, in LTAC, so match goal, this turnstile represents the line. And everything to the left of the turnstile represents hypotheses above the line. And here we don't care what the hypotheses above the line are, so I leave that blank. And everything to the right of the turnstile represents the term below the line. And we're going to match that term. It better match, that term better look like this. Well, it does. It's a match C with. When you want to bind a wildcard pattern to a variable in an LTAC pattern match, you have to use a question mark, which is different from the way variable binding works in the logix match, just to help things be confusing. Okay, so if the goal looks like match something with red do this and black do that, quantity not equal to something, right? So this is from here to here is what the proof goal has to look like, and it does look like that. And by the way, whatever expression you found right here, bind it to the LTAC pattern variable, C, which I could have called anything. I didn't have to call it the same as that. I called it the same as that just to be confusing. Okay. If you find that, then this match goal width actually succeeds, so far at least, and then it applies this pattern, this tactic, destruct C. This could fail, in which case we'll try another branch of this match. There aren't any more branches, but this could succeed, destruct C. So let's run this. Okay, we had 3 cases, remember? 1 out of 3. This is case 1 out of 3. We destruct C. Now we have 4 cases. That's not surprising. Okay, we destructed C. And we have this much simpler expression to prove. Let's do it by case analysis on S1. All right, so this is not a match on red and black, it's a match on E and T. So we could do this kind of match goal. Match goal with, well, if you have some tree, call it S, and you're matching on, E do this and T do that, and the whole thing is not equal to something. Let's look over here, right? The whole thing is not equal to something. In that case, if your goal looks like this, then do destruct S. So let's do that. We have 4 cases, but now we have 5 cases. This case analysis is going great. Okay, so here's another tree to do case analysis on. And so let's actually do this same tactic again. Just that one, we'll do it here. Okay, and now, if your goal, let's do this in the match goal. If your goal looks like prove that T is not equal to E, then solve it by doing apply T not equal to E. Okay. Well, let's start that proof over again. We get to here with the big, hairy thing to prove that this whole thing is not equal to E. And we have 1 proof goal. That's nice. We're going to do a repeat. Repeat. If your goal looks like this, destruct X. If your goal looks like this, destruct C. If your goal looks like this, destruct S. Okay, and keep doing that. And if your goal doesn't look like one of those things, then the match will fail, which makes the repeat succeed with doing nothing. Okay, so in each sub-goal, right, keep doing that repeat until you can't do any more. So there we go. 117 cases, and a lot of them look really easy to prove. T not equal to E. Okay, so let's prove all those cases. 111 cases to go. 107 cases to go. All right, when I was doing this proof by hand, I was wondering whether there's an infinite number of cases, but the answer is no. 117 only feels like infinity. Okay, so now let's do this proof again, but we'll add this. If your proof goal is T not equal to E, let's apply this T not equal to E. All right, so No more sub-goals. All right.